All right, let's do some of these clicker questions. Just sort of the basic properties of charge. Two charged balls are repelling each other as they hang from the ceiling. What can you say about their charges? One is positive, the other is negative. Both are positive, both are negative, or both are positive or are negative. Top about 32. Still missing somebody. There we go. Very good. From this picture, what can you conclude about the charges? And also in this picture, these are two isolated incidents, so these two situations are separate. So what can you say about these charges? All right, I'll stop at 45. 45. Just guess if you're not sure. Good. Let's see. The way I always like to do these is I just see. I think C's the right answer. Just go through and imagine what if this one's positive, that means this one must be positive, and if this one's positive, then that one's also positive, right? Because they're repelled from one another. And similarly, if I say this one's negative, that one's negative, if this one's negative, then that one's negative. So they all have to be the same charge, right? Because they're repelling one another. A metal ball hangs from the ceiling by an insulating thread. It's attracted to a positive charged rod. The charge of the ball must be what? There's a metal conducting ball. What must be the charge of the ball? Positive, negative, neutral, positive or neutral, negative or neutral. We've had a very similar question, maybe identical. Yeah, guys, if you have your book, these questions are at the back if you want to follow along here. All right, I'll stop at 40 seconds. 40. Okay, very good. So you can set up an induced charge. If it's negatively charged, they're going to attract. But if it's also just neutrally charged, like the copper wire we had last time, you get an induced charge where you get negative charges over here and positive charges there, and then it's attracted to the positively charged rod. Two neutral conductors are connected by a wire right here, and then you bring a positive charged rod, but it doesn't touch. The wire is taken away, and then the charge is removed, or the wires removed between them. What are the charges on the two conductors? About 1:15, we're going to stop. Don't know, just guess. I think that's everybody now. 5. Yeah. Okay, let's see. So when I bring together this positive rod here, I get a negative charge there and a positive charge there. And then when you take away the wire in between, I keep them. and then when you take away the positive charge rod, you keep those charges. This is called charge by what? Induction, right? Not conduction. Conduction requires contact, and in this case, it's charged by induction. So let's see, what was that, C? Yeah, C. Alright, we'll come back to this after we do Coulombs Law. Any questions about that part? No? I think it's pretty basic. You seem to get it okay. But if you have trouble with it, these sort of basic principles of charges, please let me know. It becomes important when we get into Coulombs Law and looking at fields and what have you. I also want to mention, I sent an email out yesterday, but I added the chapter 0, I'm calling it now, the gravitation problems. They're here. The one that I posted here is slightly different. I changed one of the numbers, like I think I changed this number right here because it made the values come out a little more even. And I changed one, maybe, in the very last problem, the large flat sheet, it didn't have a mass, so I included the mass. Alright, there are also, for some of these latter problems, you need a lot of things about the planets, like about the mass of the Earth, the radius of the Earth, the mass of Mars, and stuff like that. And that's not given here, but on the exam, I give you any of those constants. So I include them in the video, but if you can also find them on Google or whatever. I also included, went and did the solutions yesterday. So this is just like a YouTube video of me going through it. I was using a new computer for this, so I'm not sure how the quality will come out. I think it's pretty good, but I'm not sure. And plus my daughter, she was sick, she was sort of coming in and out while I was doing it. So if there's something going on in the background, that was why. Alright, I would work through those problems. That would be a good indication of what you'll see on the exam, something similar to those. And also the problems will be similar to what we'll see in the next couple of chapters, with electric fields, electric forces, and electric potential. So that's really the reason for us doing that, is just to prepare for chapters 2 and 3, chapters 1 and 2. Alright. Alright, let's continue on with Coulombs Law. This is going to look a lot like what we did with the gravitational law. It's basically the same form, just slightly different numbers that we're dealing with. Coulombs Law just describes the forces between two charges. Its equation form is F, the force, this is the magnitude of the force, so I'll write it like this, is equal to K times Q1 times Q2 divided by R squared, where R is the distance between them. And actually here we're taking the magnitude of these charges. We'll see that along the way, that whenever we use charges in Coulombs Law, we don't include the sign of the charge. Right, but I'll show you how the sign of the charge is included. The distance R is just the distance between them. Coulomb's constant, you don't have to know this. This is on your equation sheet, but it's a useful number to know. It's 9 times 10 to the 9th. Well, it's probably only useful like if you're using Coulomb's law, right? Otherwise, it's not that useful. Anyway, Coulomb's constant is, let's see, it's Newton meter squared per Coulomb squared. And Q is in units. I don't know if I've told you all the units of charge, but units are coulombs. Q is in units of coulombs. At the capital C, and then of course R is in units of meters. So remember your metric prefixes, okay? Charges are often really small, so we need to remember especially those small prefixes. Our micro is 10 to the what? Micro? -6, right? Nano is 10 to the -9. That's an easy right? Nano, 9, and then also we'll need to remember our centi, because sometimes we'll express the distances in centimeters. Centi is 10 to the -2. So don't forget those metric prefixes. They're responsible for them. Micro is 10 to the -6. Nano is 10 to the -9. And then also centi, like a centimeter, is 10 to the -2. You'll need to know the others as well, but those will come up a lot as we're dealing with charges, especially the micro and nano.
Something lowercase c.
Right, lowercase c, just like in centimeter. All right. Go down from here. I'll wait just a second. Hey, my kid won first place in the social studies fair. Isn't that cool? It was on the tornado in Joplin, Missouri. We have family in Joplin, so his aunt and uncle lost their house. And so he had pictures of the house, he did interviews with them, and all sorts of stuff. It was really cool. He's very pleased with himself. Alright, want to go down from here? Oh, that's where we need to go. There's your equation sheet, by the way. If you have your book, your equation sheet is in the back. Although I haven't yet included the chapter 0 equations. I'll do that soon. Alright, so Coulombs law is very similar to Newton's universal law of gravitation. Remember, we have Coulombs law, K, Q over R squared. And if you remember, the law of gravitation was G, M over R squared. So they both share that 1 over R squared dependence. They both share that dependence on two quantities, whether they be charge or mass. And they both have this constant, K or G. So everything that we do with Coulombs law will be the same as what we did with the universal law of gravitation. And everything that applies to that law will also apply to Coulombs law. We also see that Coulombs law, or the third law, Newton's third law, also applies. So that if I have a force on one charge, then I'm going to have that same force on the other charge. And we saw this with the law of gravitation. The only difference here is that with the law of gravitation, the forces were always what? Were they always either attractive or always repulsive? The forces in the law of gravitation. Right, masses always attract one another. And that's not so with charges. With charges, it depends upon the magnet or the sign of the charge, whether they're attractive or repulsive. And this is where it comes in with Coulombs law. When we use the magnitude of the charges, we don't include the signs. We're accounting for the signs when we draw the direction of the vectors. So for example here, if I have a force on Q1, it's going to be to the left or right? To the left, because I have two positive charges. They're going to be repelling one another. And then Q2 will have a force in that direction. So I'll call this the force on particle 1 due to particle 2. And this is the force on particle 2 due to particle 1. And these are going to be equal in magnitude. Actually, in vector form, one will be the exact negative of the other. And then similarly down here, if I have a force on Q1, it's going to be in that direction, and the force on Q2 will be in that direction. Because these are different charges, so they're going to attract. So it goes back to those basic principles of charges, that like charges repel and opposites attract. Just like we had with the law of gravitation, the superposition principle applies. That is that if my net force, superposition principle is just that the net force is just the sum of all the forces, the vector sum of all the forces. And so we'll do this once again, where we add up forces. We'll do a 1D problem and a 2D problem. You could see either. You will see a 2D vector problem, but you could also see a 1D vector problem as well. So let's do first a 2D vector problem. I think y'all are old hand at this now, right? Like when you see this on the test, which you'll see a vector problem, you'll either see it as a law of gravitation, or Coulombs law, or electric fields, which we'll get into next. And y'all are all going to get perfect scores on it. It'll be 2 or 3 particles in 2 dimensions. Yeah, perfect scores. That should be an easy 15 points for you on the exam. Yeah? Yeah, okay, yeah. All right, so let's do an example. Let's say that we have these charges. I have a 2 Coulomb charge. You might not be able to see that very well. 2 Coulomb charge a -1 Coulomb charge and a 4 Coulomb charge, and I want to know what is the net force on this charge. So the first thing I want to do is just draw my vectors. I have two vectors, and go ahead and draw what are the vectors. The force on particle 3 due to particle 1. Is it attracted or repelled from that particle? And what is the force on particle 3 due to particle 2? Is it attracted or repelled because of that particle, that negatively charged particle? All right, so first thing, we just draw our vectors, and then we want to calculate the magnitude of those vectors. So if I were to draw my vectors here on Q3, I'd have 2. The one due to this particle, Q1 plus 2 coulombs, would be to the left or right? It's going to be to the right, right? They're repulsive. This is a positive particle. This is a positive particle. So those two charges are going to repel one another. So it is going to be to the right. I'm going to call that F3, 1, the force on particle 3 due to particle 1. And then what is the direction of the force due to this particle on this particle? That one's to the left. They're attractive. They're attractive because why? Why are they attractive? Opposite charges, that's right. So, and then also I'm going to go ahead and draw it with the correct magnitude. Will it be bigger or smaller than F31? And if so, by what amount? Is F32, the force on particle 3 due to particle 2, going to be bigger or smaller than F31? And if so, by what amount? It's going to be smaller, you're right. By what amount? No, not by a factor of 4. Oh, actually, let's see. It's not so obvious, is it? Because I forgot we have these distances. I was just looking at the charges. I'm sorry. Let's we'll just go ahead and calculate them. But let's see. Yeah, it's not so obvious because not only F2, or excuse me, Q2 is a smaller charge, but it's closer. Is that what y'all were thinking? That you have to account for the distances. Yeah, the distances and the charges. All right, so let's just go ahead and we'll just draw F32 like that. Don't know right off if it's bigger or smaller. All right, now we want to calculate F31 and F32. F32 is K Q3 Q2 over R squared. I'm not going to draw the absolute value signs whenever I write Coulombs Law, but we'll just remember that those are always to be the magnitude of those charges. So I'll leave off the signs. That's 9 times 10 to the 9th. Q3 was 4 coulombs. Q2 is 1 coulomb. Remember, no negative sign there. Divided by, what's the distance between 3 and 2? Right, 2 meters squared, right? So this cancels there, and we're left with 9 times 10 to the 9th. And then similarly, I can look at F31. That's going to be 9 times 10 to the 9th times Q3, which is 4 coulombs, times Q1, which is 2 coulombs, divided by what distance? Right, 3 meters squared, right, which is 9. This 9 cancels with this 9, and we're left with 8 times 10 to the 9th. All right, so F31 is 8 times 10 to the 9th. F32 is 9 times 10 to the 9th. I can do the sum of the forces. Is F31, which is to the right, so it's positive, minus F32, which is to the left, so it's negative. That's 8 times 10 to the 9th minus 9 times 10 to the 9th. So I'm left with a net force of 1 times 10 to the 9th newtons. All right, So that's the answer to that one. Basic 2D problem. We've had those before. We had them last semester, but the forces were all a little bit different. All right, like we weren't dealing with electrical forces. Yeah,
So that
Josh?
means that F31 is weak, I guess, weaker than F32.
That's right. It's yeah, because let's see, how did that work out? Q1 is a bigger charge by a factor of 2, but it's further away, so it works out that yeah. All right, let's do a 2D problem. I'll go down from here. You'll see in your homework for the gravitation that often I'll use numbers that will or you can use numbers that will make the problem a lot easier. So there's actually a problem in the chapter 0 homework where you have 5 different particles, but if you notice you'll notice the symmetry, which allows you to disregard some of the vectors, and it makes the problem a lot easier. If you don't notice that, it makes it a little more difficult. But you should try to look for those things on the exam. What are things that I can use to make this problem easier? What are some things that I can disregard the forces? You'll see what I mean when you start that homework. Have y'all started the homework yet? Are you finished? Okay. Yeah. Well, the chapter 0 isn't in there. It's only on the website. All right. Superposition principle can be in 2 dimensions as well. So let's say I have this collection of charges. This is Q2. It's -2 nanocoulombs. This is Q3. It's 1 nanocoulomb. And this is Q1. It's 3 nanocoulombs. Y'all can see the white okay? Yeah? Christian, you can see it as well? Yeah, okay, I'm going to erase that. All right, I want to know now what is the force on Q3. So the first thing I'll do is draw my vectors. So go ahead and draw the vectors that you would expect for the force from Q2 and the force from Q1. So that is F32 and F31. And then we'll calculate the magnitude of those. While you're drawing your vectors, I'm just going to write this F32, the magnitudes of F32 and F31. Feel fine? All right, what are the forces on Q3? Is it attracted or repelled to Q2? It's attracted, so the force is to the left. So this is F31. And attracted or repelled from Q1? It's repelled, so my force is up and in this direction, so that's F32. Then we'll need to find out what are the angles. So if I were to draw my coordinate system, and whenever we're dealing with forces in 2 dimensions, we need to establish what is our coordinate system. So I need to figure out what is this angle theta. And in order to do that, I can recognize that there is a triangle right here, all right? And that whatever this angle is equal to this angle. Right? Anytime you have 2 lines crossing, the opposing angles on either side are equal. So if I find this angle, then I can find what this angle is. Does anybody know what this angle is right off? This is a special triangle. It's useful to know it. It's not 60, no. It's not 30. 37. It's not 45. Y'all throwing out all the special triangles there. It's 37 because it's a 3, 4, 5 triangle, and the angles on those triangles are 37 and 53. I know this one's 37 because it's opposite the smaller side of the triangle. So if you forget that, I mean, not everybody knows the 3, 4, 5 triangle, and that's okay. But if you forget it, just remember that you can do the inverse tan of opposite over adjacent. Isn't that right? SOHCAHTOA, opposite over adjacent. That's 3 over 4. And you'll find that that's 37 degrees. So if you forget your special triangles, that's fine. Although it's very useful to know those triangles. I use them a lot. All right. So if that's 37 degrees, then this angle is also 37 degrees. All right. So now we want to figure out the magnitude of our forces. I'll do the first one. I'll write it out, and then I'll just give you the answer for the second one. F32 is 9 times 10 to the 9th. That's K. Q3 is what? 1 nanocoulomb? So that's 1 times 10 to the minus 9 coulombs. Q2 is 2 times 10 to the minus 9 divided by this distance, which is, 4 meters squared, or 16. And then that's equal to 1.13 times 10 to the minus 9 newtons. I'm keeping more sig figs than I need here because it turns out that the forces are very similar, so just to differentiate between the two. And then if you find F31 with the thought here that R for F31 is equal to 5 meters, because this is a 3, 4, 5 triangle. But again, if you forget that special triangle, of course, you can do the square root of 3 squared plus 4 squared. And F31, I'll just take a quick moment to calculate what is F31 and tell me what you get. I'll try to use numbers that give you nice round answers. These aren't nice round answers, but usually I try to give you nice round answers for the test. Do you have an answer? 1.8 or 1 point? You're sure? 1.08. That's right. Yeah. So the answer here is 1.08 times 10 to the minus 9 newtons. All right. This is pretty easy for y'all. It's a lot like what we did for gravitation. So hopefully it's straightforward. All right. So now that we have the magnitudes, and we have the directions up here, we just go through that old practice where we resolve our vector into its x and y components, add the x components, add the y components, and then find the magnitude and direction. So it looks like this. I have a vector in this direction at 37 degrees. It is F31 1.08 times 10 to the minus 9 newtons, and then I have another vector in this direction that's 1.13 times 10 to the minus 9. I want to find the x component here. That's going to be this value times cosine of 37. Let's see, I think I have that. I don't have that. And then I also want to find the y component, which is 1.08 sine of 37. Excuse me, 1.08 times 10 to the minus 9 sine of 37. Whatever those values are. All right, and then I subtract these two numbers. I say the sum of the forces in the x direction equals the difference in those. That is F31 cosine theta minus F32. That's this number minus this number, and that gives me I get negative 2. If somebody could check this, though, I think I might have had a mistake here. I get negative 2.67 times 10 to the minus 10 newtons. That is this minus this. And then the sum of the forces in the y, there's just one force in the y direction, and that is equal to 6.50 times 10 to the minus 10. This number is correct, the 2.67? Yeah, okay, thank you, Harlan. All right, so those are my x and y components of my forces. So if I draw those, I have one in the x direction, I have one in the positive y direction. So my resultant vector, which is what I want to know, will look like this. I want to know this angle, I'll call it phi, and I want to know the magnitude. Okay? Alright, so to find the magnitude, I say the square root that squared plus that squared. And when I do that, I get 7 times 10 to the minus 10 newtons. And then to find the angle phi, I do my inverse tan of opposite over adjacent. That is the y component divided by the x component. Remember, there are lots of different ways to do this. You can include the sign or not, and depending on your calculator, it may or may not get it right. But I usually just leave the signs off, and then I just go with what my picture looks like. This works out to be 67 degrees, and you need to add a qualifier to that. It's above the negative x-axis. Or you could say it's what, 90 plus 23, 113 from the positive x-axis. However you want to do that. Be careful with your calculator. I think you all know what your calculator does by now with regards to these angles, because sometimes it can give you the wrong answer. Alrighty? I know we've done vectors a lot, like from last semester, and we're going to do them once more with electric fields. You'll certainly see it on your exam, and we'll see vectors again towards the end when we get into magnetic fields and induction and what have you. But it's an important thing, especially for you engineers. You're going to take a whole course where you're dealing with vectors like this, and you'll get into it in quite a bit more detail. Alright? Y'all feel comfortable with this? Hopefully this is an easy 15 points on the exam, either in the form of gravitation, electric forces, or electric fields, which we'll see soon. We'll do one more example, and then there's an example in your homework as well. Y'all don't look as excited as you should be about the opportunity to add vectors, because it's very important for a lot of different things. Okay. It's a little boring though, isn't it? I know it's early. Okay, let's do this clicker question. You'll probably see a multiple choice question, something like this. Consider this configuration of charges. Which vector best represents the net force acting on the rightmost charge? If you finish this one, you can go on to the next one, if you have your book. The next multiple choice question. I'll stop about 135. Looks like we're still missing one person out there. Just guess if you don't know. Alright, very good. He is right, I think. Okay. Let's see, so you just want to draw your vectors. These two charges are going to be repelled in that direction, but these two charges are going to be attracted by a greater amount for two reasons. One, this 4q charge is bigger, and these two charges are also closer. So my second vector will look like that. If I add up those vectors, I'll get something right here. E is the right answer. Let's try this next one. Wait, I thought I had another one. Is it on the next page? Oh yeah, there it is. Let's do this one first, and we'll come back to that other one. What is the magnitude of the force on the 6 nanocoulomb charge in this figure? If you can't see that, this is a 3 nanocoulomb charge, and this is a -6 nanocoulomb charge. We'll know the magnitude of the force on that charge. You'll use Coulombs Law to find this, but in the course of that, you'll also need to find what is the distance between the two on this equilateral right triangle. Alright, I'm going to stop at about 3 minutes. About 10 more seconds or so. There's a few more of you out there. I'll go on to 3:05. That's everybody. Okay, good. That's what I got too. These are pretty straightforward. You just want to find the force between the two. That force is kqq over r squared. It's 9 times 10 to the 9th. Q is 3 times 10 to the minus 9. 6 times 10 to the minus 9. Divided by the distance squared. You have to find the hypotenuse of this triangle. The square root of a half squared plus a half squared is 0.71. So 0.71 meters squared, and then when you do that, you get 3.2 times 10 to the minus 7 newtons. All right, well, let's try this quick test problem. I'm going to make it a little bit simpler. It's likely on your test you won't see something like this unless it's unless you can simplify it in some way, because to go through all those steps that we did before would probably take too long, and there are just too many places for error. So let's do one where I want to know not just the magnitude and direction of the force, but also the force on particle Q1 just due to particle Q3. So let's just get rid of Q2. So let's look at part A, and then that should take us to the end. And then we'll look at part B next time, I think. All right, so what are the magnitude and direction of the net force acting on particle Q1 due to particle Q3? And then also I want to know not just the magnitude and direction, that comes pretty quickly, but I also want to know this expressed in vector notation. All right, I'll give you a few minutes. First thing you want to do is identify the vectors. You want to calculate the magnitude. That comes pretty quickly. Just you need to find the distance between the two and use Coulombs Law. Right, Q2 does not exist anymore. I speak. So express the magnitude and direction of the vector, and then also the vector in vector notation, the ij notation. You'll want to draw your vectors on Q1, or your vector, rather. Identify any angles that are relevant. A couple more minutes, and I'm going to start writing down the solution. magnitude yet? Courtney, you look like you have it. What is it? It's okay if it's wrong. What is it? Oh, no, that's the right numbers, but the exponent's not right. You're right, -3, yeah. So I get 0.022. So you had an exponent wrong there somewhere. 9 times 10 to the 9th. Q1 is 2 times 10 to the minus 6. Q3 is 3 times 10 to the minus 6. You had one of those exponents wrong, I'm not sure which one. And divided by the distance squared, which is 5 meters squared. And it's 2.1 something times 10 to the minus 3, 0.0022 newtons. Does anybody have the angle for the force? It's okay. What is it, Mark? Oh, I'm not worried about Q2. Yeah, Q2 doesn't exist. But there is a force on this Q3, and I want to know what is this angle right here. It does matter to find the magnitude and direction. Right, that's 30. That's that special triangle. Right, so that theta is 37 degrees above the negative x-axis. Right, so that's the that's my first answer. Anybody done the x and y components yet? In vector notation? Okay, find the x and y components. Notice that one of your components is negative and one of the components is positive, so you need to reflect that in your answer. Yeah. Oh, yeah. Oh, it's a lot easier than doing on I would do this. I think you're adding this extra factor. Alright, let's see. Anybody have the x and y component too? X component? Oh, what's up in there? What's the x component? Hunter? Oh, come on. Zach, you know it? Zach? Zach? Okay. Alright, well, I want to find the x component, right? The force in the x direction is just going to be 0.0022 times the cosine of 37. And the force in the y direction is 0.0022 sine of 37. One of these is negative. Which one is it? The x or the y component? The x component is negative, right, because this component of the vector is in this direction. The y component's in that direction. I don't know what these values are. Can you tell me? Uh-huh. All right. Have agreement? At least one person on it? Yeah, that looks good. All right, so that's your x and y components. Let's see what time is it. We don't have time to do this one, but let me just sort of set us up for the next one. Now I want to know what are the x and y coordinates for a charge plus 3 microcoulombs placed at the net force, so that the net force on Q1, actually let's do Q3, is 0. And before we go, I just want to think roughly, where do we want to place this third charge so that the net force on this charge is 0? Roughly, where do we want to place it?
Down to the right.
That's right, we want to place it somewhere down here, so that way we have a positive charge here, a positive charge here, and then have a negative charge in between, and they're both going to be pulling on it, and next time we'll figure out what is this charge need to be placed so that the force on this charge is 0. Alright, or if you get bored between now and then, you can do that, you know, in your free time, or whatever. Alright, so we'll do that next time. We're going to place a charge here. Have a good day. I'll see you Friday.